Hi there. So today I'm going to talk about section 1.3, which is the beginning of our talk about linear functions. Now, one of the things that I'm going to mention is in this course, there is the assumption that you guys have played around with linear functions before. Okay, so I am going to teach you the material, of course, and go through many examples, but I am going to make the assumption that this is at least vaguely familiar, even if it's been a few years. Okay, so section 1.3, we have linear functions. If you haven't noticed, this book takes very much of an applied approach to these things. So I will take the applied approach, but I will show you some problems that are very nuts and bolts. Okay? Now, in section 1.2, the last section that we did, we looked at the average rate of change on some interval of a function. Okay? Now, for a lot of functions, the average rate of change is going to vary depending upon the interval that you're looking at. For example, if you have an increasing and decreasing function, well, here the average rate of change is positive, remember, because it's an increasing function. And for example, if we wanted to find the average rate of change between these 2 points, well, it's going to be negative because it's a decreasing function. But one really cool thing is that there are a class of functions that no matter which interval you look at, the rate of change is always the same. And lo and behold, those are our linear functions. So the cool thing about these, well, one of the cool things about these is that no matter which interval we're looking at, the rate of change is always the same. So what I'm going to do is start out with just a word problem example, and we're going to kind of pick it apart a little bit, and let's do it. So, to get a car towed, it costs $40 to have the service come, plus they charge $2 per mile that the car needs to be towed. Sort of like having an electrician or a plumber come out to your house. They charge you just for gracing you with their presence, just for coming, and then they charge you per hour. Well, towing companies work in a very similar manner. Just to see them, just to have them come out, they have that base fee, okay? And then, depending upon how many miles they need to tow you, well, they charge that much per mile. Okay? So, some questions we could ask is the following. We could ask, what is the average rate of change of the cost? Now, you may seem a little perplexed because I didn't actually give an interval, but that's okay. This is actually a linear function, okay? But we can just play around with a few different intervals and you'll see that we get the same thing. For example, how much does it cost just for them to come there? No towing at all. Doesn't that cost $40? Yes. How much does it cost for them to tow you 1 mile? So how about for 0 miles, we can actually make a table. How about we do that? So 0 miles, so this is miles, and then we'll do cost. Okay? So for 0 miles, it costs $40. If they tow us 1 mile, well, it's that 40, but Don't they charge us $2 a mile? So it'll cost $42. And we can actually keep building this table if we would like to. Let's go up to 5 miles. So 2, 3, 4, and 5. So if they tow us 2 miles, well, it's $40 for the base fee plus $2 for 2 miles. Well, it's going to cost $44. If they tow us an additional mile, well, it's going to cost us an additional $2, so $46. If they tow us 4 miles, well, that's 1 more mile. So add on $2, you get $48. And then here I claim you get $50. So what is the average rate of change of the cost? You could pick any one of these intervals. I'll just pick these two. Isn't it the change in cost over the change in miles? So we get 2 over 1, which is 2. Okay? Remember, it's the change in the function values divided by the change in the independent variables. Okay? All right. Now, if we wanted to graph something that looked like this, we could certainly do that here. Notice our independent variable are the miles driven, and the dependent variable would represent our cost. And we can just go out to 5 miles. So here's 0, 1, 2, 3, 4, 5. And let's have this be 40. And then we could go 42, 44, 46, 48, 50. So at 0, we're at $40. 1 mile later, we go up 2, we go up 2, and I claim if you connect the dots and we draw a straight line, this is what our graph is going to look like. Now, one of the things that we're really going to be interested in is taking something like this and writing a formula for it. Okay? So one thing I want you to note is the following, at least in this scenario. Isn't the total cost equal to the initial cost? Or you can think of that as your flat fee plus the cost per mile times the number of miles driven. So our initial cost here is 40. The cost per mile is 2, and we can call the number of miles driven X. Okay? Now, when you talk about a cost per mile or some sort of ratio, we can think of that as our variable cost. But I want you to see something here, okay? Because actually we just came up with the formula, and this is what our lines actually look like. But I want to liken this to something, okay? Notice my number out here. Wasn't that our flat fee? More specifically, wasn't this the cost to drive 0 miles? Okay? Now, what is that point called when your X value is 0 and you're looking at your Y value? That's called your Y-intercept or your vertical intercept. And notice this number in front of our X, that was our cost per mile. Notice that's exactly what we got for our average rate of change. That also is not a fluke. Remember, from section 1.2 when I talked about this, the average rate of change is actually the slope of your line. Remember, it's your change in Y values over your change in X values. So, what I want to do for a little bit is play around with our basic function of a line And as we go, we're still going to be playing with lines in section 1.4 and 1.5. But when you have something written as a line, I'm sure you guys have all seen y equals mx plus b. It's very reasonable to ask, what do m and b tell us? Okay? So, some things that I want to point out and remind you. M, you'll probably recall, is your slope. That's the rate of change. It's the change in y values over the change in x values. Think of it as your average rate of change. Your b is essentially your flat fee, if you will, but that, guys, is your y-intercept. Now, if you don't remember what the intercepts mean, I will keep going over this throughout the semester, but a y-intercept is where your graph touches or crosses your y-axis. Specifically, it is where x equals 0. Okay? As a side note, don't worry about this at this point. Your x-intercept is where your graph touches or crosses your x-axis. Now, since I mentioned it, I can't help myself, okay? Our graph is going to cross our x-axis over here, which is pretty meaningless, okay, because we can't really go a negative number of miles. But, you know, we need to be pragmatic about things. In order to find our x-intercept, if that's where our graph touches or crosses our x-axis, we can ask ourselves what is always true, no matter where we are on our x-axis. And I think you'll grant me we have not gone up or down. It's where y equals 0. So if you're talking about your x-intercept, it's an ordered pair that looks like this. And similarly, if you're talking about your y-intercept, it's an ordered pair that looks like that. In other words, specifically where x equals 0. Okay? Now, just so that we're all very refreshed, I want us to practice finding the slopes of 4 different lines. Okay? And then we're going to look at patterns. So much in mathematics is about patterns. Okay? So, what if, for example, I want us to find the slope of the line containing these points? Now, whenever I think of slope, I always think of, you know, like biking up a hill. Okay? When you're talking about the slope, as you guys have probably studied before, you're talking about the steepness, okay? And just very quickly, I want to motivate our formula for the slope, okay? So this could be one hill we're going up, and this could be another hill. I think you will grant me that biking up this hill is very different than biking up this hill, okay? So, how can we look at these? Well, let's call this point x1 and this point x2. If I want to look at the slope of this bottom line, essentially what I'm saying is, well, as I move from x1 to x2, as I'm moving this horizontal distance, when I'm talking about the slope, I'm asking how much does my vertical distance change? Okay? And I can do the same thing with these two x values on this other line. And I think that you will grant me that here my y values change, my vertical distance changes a heck of a lot more with this same horizontal distance. So when you're talking about your slope, you're talking about essentially the change in the rise over the change in the run. That's where people get rise over run from when they talk about slope. Now, When you're talking about the change in the rise, you're talking about the difference between two y values. I mean, if we just take these points, let's pretend this is x1, y1, and this is x2, y2. What is this vertical distance change? Well, I claim this distance up here is y2. This distance down here is y1. And then this distance here I claim is x2 minus x1. Okay, right? Because this whole thing is x2, but we're not interested in this distance, which is x1. Okay, that's where your slope formula, y2 minus y1 over x2 minus x1, comes from, if you're given two ordered pairs. Now again, we played with this using our average rate of change. So, let's find the slope of the line containing these points. Ready? It's the change in y values, so I can say it's 11 minus 5 over the change in x values, so 7 minus 3. So I get 6 over 4, which is 3/2. Okay? Notice we got a positive slope. If you're wondering, what does a line with positive slope look like? Think about the average rate of change. When your average rate of change is positive, remember your function is increasing. So if you wanted to graph these points, we could say, well, 3, 5 is 1, 2, 3, 1, 2, 3, 4, 5. And then 7, 11, well, 3, 4, 5, 6, 7. And that was 5, 6, 7, 8, 9, 10, 11. Well, there's our two ordered pairs. We can play connect the dots. And sure enough, we have an increasing function. All right, what if I want to find the slope of the line containing the following points? How about -1, 4 and 3, 1? Again, we look at the change in y values over the change in x values. Now, there's nothing saying you have to start with the further ordered pair. I could start with my 4 and do 4 minus 1, but note, if you start with this y value in your numerator, you have to start with the corresponding x value in your denominator. Therefore, our denominator would be -1 minus 3. 4 minus 1 is 3 over -4. Notice we got a negative slope. Our slope is our average rate of change. So presumably from what we saw last time, if we have a negative average rate of change, in the back of our heads we're thinking, it's a decreasing function. Well, let's check it out. If I want to plot these points, I've got -1, 1, 2, 3, 4. And then I have the point 3, 1. Play connect the dots. Pretend I actually drew a straight line through the points. But notice as we move from left to right, lo and behold, again, it's a decreasing line. All right, there's two more I want to do. I want to do these because we're actually going to be going somewhere with it, not in this section, but in our next section. So, let us now find the slope of the line containing the points 2, 1 and -3, 1. All right. Again, to find the slope, It's the change in y values over the change in x values. I'll start over here. So in my numerator, I'm going to get 1 minus 1. And in my denominator, I'm going to get negative 3 minus 2. Well, in my numerator, I have 0 over negative 5. And 0 divided by any number is 0. Now, perhaps you're wondering, what does a line with no slope look like? Well, think about biking on, say, a road with no slope. Doesn't that mean that it's perfectly level? Okay? And if we wanted to graph this line and see what it looks like, let's check it out. Well, we've got the point 2, 1. We've got the ordered pair negative 3, 1. Again, we can play connect the dots, and sure enough, it matched our intuition. Moral of the story, when you have a slope equal to 0, knee-jerk reaction. We got ourselves a horizontal line. Okay? Now, I can't resist one more example. Imagine that. So, suppose I want to do this example now. Suppose I want to find the slope of the line containing 1, 7, and 1, 3. All right. Again, it's the change in y values, 3 minus 7, over the change in x values, which is 1 minus 1. In our numerator, we get negative 4. In our denominator, we get 0. All right, a red alert should be going off in everybody's head. Remember, it's mathematically illegal to divide by 0. Okay? So we say this is undefined. Now, if you're sitting there wondering, wow, I wonder what a line with an undefined slope looks like. Well, wait no further. Let's check it out. We've got the point 1, 7, so 1, 1, 2, 3, 4, 5, 6, 7. And we have the point 1, 3. We play connect the dots, and we have a vertical line. So a slope equal to 0 is a horizontal line. An undefined slope gives us a vertical line. Isn't that fun? I think so too. Okay, and then you think about, well, how do you bike up this? No, this is called free fall. You don't. Okay, so next, what we're going to do is we're going to be playing with a bunch of different lines, and there's different ways that we can actually find the equations of lines, and we're going to be dealing with that more in the next section. However, I would like to take us through some examples right now. Okay? Now, there's two general formulas we can use to find the equations of lines, and one of them is the one that you're all probably very familiar with, y equals mx plus b. Okay? There is another formula for finding the equation of a line, and I want to show it to you. Okay? And I'm really happy that we just happen to have our slope formula right here. Okay? I'm going to write this the same but different. Okay? You might wonder why. That's all right. You'll see. I'm going to say my numerator is the change in y values. My denominator is the change in x values. Oh yeah, I'm calling this my slope. What's the difference? Well, notice I bebopped things on opposite sides of my equality. And then the other thing that I did is instead of putting the subscripts of 2, I just left it blank. Okay? So, here's our formula for our slope. Now, Pretend I thought to myself, wow, I would really like to write this, but I don't want a fraction. Well, how do you get rid of fractions? What you can do is you can multiply both sides by your denominator. Remember, equations are like kids. Whatever you do to one, you got to do to the other. All right? So, why did we multiply both sides? Well, I think you'd agree on my right side, I have m times the quantity x minus x1. It might not look pretty, but it is okay. Now, if I multiplied my left side by this, notice those cancel, and I'm left with y minus y1. Essentially, what we did is we rewrote our slope formula in a different way, okay? But this is another way that you can find the equation of a line. This here, you guys have seen, is called your slope-intercept form. And this one here is called your point-slope formula. Okay? This is slope-intercept because m is your slope and b is your intercept. And this one you can use as long as you have a point and a slope. Now, on any test, I will not tell you which formula to use to find the equation of a line. I want you guys to do whatever jives better in your brain. Some people have a strong preference for one, and some people have a strong preference for the other. Okay? The thing is, no matter which way you do it, as long as you do everything mathematically correct, you're going to get the same answer. So what I'm going to do is I'm going to take us real quick through an example of finding an equation of a line. And what we're going to do is actually do it both ways. Okay? I'm going to reinforce this more in the next section, but this is a really important groundwork to get laid. So, suppose I want to find the equation of the line passing through. How about this? -1, 1 and 1, 3. Okay? No matter which way we do it, we gotta have a slope. Okay? But we're in luck because given any 2 points, we can certainly find the slope. So, step number 1, no matter which way you want to find your equation, you gotta get your slope. Let's do it. The slope is the change in y values over the change in x values. Minus a negative is plus a positive. 3 minus 1 is 2. 1 plus 1 is 2. Wow, we get a slope of 1. Okay, now, if we want to find the equation, I'm going to show it to you using both formulas, okay? Watch me with both and then start thinking about the way that jives better in your brain, okay? So, most of you are probably more familiar with the y equals mx plus b version. So let's go through that first, okay? Now, again, you don't have to do it both ways. I just want to show you both ways so you start getting familiarity. Okay? Well, in order to find the equation of a line, we need to know what our m and b are. I claim we found our m. Didn't we get m to be 1? So we can write y equals 1 times x plus b. All right. I also now need to know what my b is. We don't know that yet, but we do have an ordered pair xy. In fact, we have 2 of them. So one reasonable question to ask is, does it matter which ordered pair we use? And I will answer no. Let's use the 1 and the 3. Okay? So 3 is my y value. My slope is still 1. Oh, my x value is 1 plus b. Don't I get 3 equals 1 plus b? So b is 2. So if I was to write the equation of the line, you can write 1 times x plus 2. In all honesty, I would just write it like this. Okay? Now, I'm going to show you using this point slope form just to show the consistency. Now, here's what you plug in this form. You plug your ordered pair in for the x1, y1, and you plug your slope in. And again, it doesn't matter which ordered pair you use. We can use the same ordered pair if we'd like. Y minus my y value equals m times x minus my x value. So we get y minus 3. Well, distributing a 1 is a moot point. And to get y alone, we would add 3 to both sides. And lo and behold, you get the same thing. All right, one other quick thing I want to say pertaining to this line. Check this out, okay? If I was going to graph this line, and we'll play with graphing a lot, I could just plot my points, -1, 1, and 1, 3. And if I play connect the dots, this is what I get. Notice it's a slope of 1, up 1, over 1, up 1, over 1. But notice something else. What did we get for our b value, for our y-intercept? Didn't we get that to be 2? And isn't that precisely where the graph crossed our y-axis? That's so cool, in my humble opinion. Okay, let's play with some more examples. Again, hopefully some of this is review for you. I'm just trying to reinforce a lot of this stuff. Okay? Alrighty, so I have about 6 examples to do, and that'll take us to the end of this section. So the first example that I'm going to do in your textbook is number 10. But what we're asked to do in this example is to identify the vertical intercept and the slope and explain their meanings in practical terms. So, what we're given is that the population of a town can be represented by the following formula. We have P of T is 54.25 minus 2/7 T. P represents the population given in thousands, and T represents the time in years since 1970. Now, we're not going to be solving anything. What's important here is just to identify what is our slope and what is our y-intercept. All right, so let's do the vertical intercept or y-intercept, okay? I think you'll grant me that the vertical intercept or the y-intercept is 54.25. I wrote it as an ordered pair. It's just my nature, okay? Now, more important than identifying it, let's talk about the meaning. Okay, remember your vertical intercept or your y-intercept is the value of y or your function when your x value or t value is 0. Do you all agree if we plugged in t equals 0, that would nix this term and we would get 54.25? Okay, the way I want you to think about your y-intercept or vertical intercept when you're interpreting these things is it's your initial value. Think of that $40 for our towing fee. Okay, So when t equals 0, in other words, in 1970, the population of the town was 54.25 thousand people. Okay? Again, when you're talking about your vertical intercept and interpreting it, it's whatever happens initially when t equals 0. Now, what does the slope mean? Yes, our slope is 2/7, and we could round that to be about 0.29. Okay? But the way that I would interpret my slope is the following. Remember, the slope is a rate of change. Okay? In this case, remember, it's the change in y value, so it's the change in population over the change in time. The way I would word this is for each additional year. In other words, as we move one place over on our graph, well, what happens to our line? In this case, since it's negative, the population decreases. Again, it decreases because we have a negative slope by 2/7. Okay? If that's funky, don't worry. We're going to be practicing a lot of these guys. In fact, we're going to do another one. The next one I'm going to look at is number 16 in your book. But again, I'll write down all of the relevant information. What this one says is in 2003, the number of SARS cases reported in Hong Kong was initially approximated by this. 78.9 plus 30.1 T. And let us say this. This N is the number of SARS cases. Remember, that was like that severe respiratory disease. And T, they're telling us, represents the number of days since March 17th. This is given in your book, okay? So what we want to do is interpret these numbers. Okay? Again, let's first interpret. Your book calls it your vertical intercept. I'm all about calling it my y-intercept. Okay? What is this 78.9? Well, that's the value when t equals 0. If t represents the number of days since March 17th, that means that t equals 0 corresponds to March 17th. So really what it says is on March 17th, there were 78.9 SARS cases. Okay, next, what does this 30.1 mean? Well, the 30.1 is our slope. Notice it's positive here. Therefore, it's increasing. So notice the pattern of how I write this, okay? So for my slope, I will again say for each additional, now I'll say day, because notice my time is given in days. For each additional day after March 17th, well, what happens? We're talking about the number of SARS cases. Here we were talking about the population. Now I'm going to say it increases. It increases because it's a positive number by 30.1 people. Okay. Well, let us do another one. Now we're going to look at number 18. And what this one says is the following. In 2012, the population of a town was 21,510, and it was growing by 63 people per year. And what we want to do is find a formula for P, the population of the town, in terms of T, where T represents the number of years since 2012. Don't let that mess you up. Actually be quite thankful for that. Okay? You may ask, why should I be thankful for that? Well, for the following reason. Okay? We're assuming that this is a linear function, so we could say P of t is mt plus b. Notice I'm just using t's instead of x's. Okay? Why are we thankful? Well, if t is the number of years since 2012, do you all agree that if I plug in t equals 0, that will give me my y-intercept? Yes. And we're given the value when t equals 0. So already we know that we have this. The next thing we have to figure out is, what is m? Well, m is the population change per year. Since we're increasing, m is positive. Okay, if it was decreasing, we'd have m be negative. So we can write 63t plus 21,510. All right. Got to do one more. Then I have a quick comment about tables, and then we're good. Now, all we're going to do right now, at least initially, is find an equation. I'm going to look at number 28. This says, a company finds that there is a linear relationship between the amount of money it spends on advertising and the number of units it sells. So money spent on advertising, number of units sold. Okay, we're saying this is our independent variable. I suppose we can independently choose how much money we're going to spend on advertising, but they found that the number of units sold depends upon that. Okay, they say if it spends no money on advertising, so no money, then 300 units sell. For each additional 5,000 spent, so let's say if 5,000 is spent, an additional 20 units is sold. So if 5,000 is spent, how many units will be sold? An additional 20. So you can say 320 units. Now, we could have written this differently, but I am trying to urge us at the beginning to just get ordered pairs right from the get-go. Okay? What this says is if $0 are spent, 300 units. If $5,000 is spent, well, they say an additional 20 units, which will give us 320. Can we find the equation of this line? Absolutely. Notice, whenever you have 0, some number, yeah, you got your y-intercept. So don't we already have y equals mx plus 300? Okay? Now, what we can do is, well, we need to find the slope of our line, and then we can just plug it right in. We can certainly do that. It's the change in y values over the change in x values. So we're going to get 20 over 5,000. Yes, this can be reduced, but there's a reason why I'm going to leave it like this for now. I understand it's not very satisfying, but I mean, yeah, this would go in here and then you'd get 1 over 250. Now I feel much better. But the reason why I'm keeping it like this is I want you guys to look at this fraction here, change in y values over change in x values, okay? And look at how it was given in the problem. Okay, for each additional $5,000 spent, it increased by 20 units. All right, now one more quick comment that I want to make is if you're given a table, it's a reasonable question to ask, how do you know if you have a linear function? Okay? We're going to be playing with this when we're dealing also with exponential functions. What I'm going to do is just write down 2 tables and we're going to compare them. So, one table looks like this. And the other table, we'll have to name him differently. We'll call him G. I want to know if either of these guys represent a linear function. Okay? Now, the hallmark sign of having a linear function is that the rate of change is the same no matter where you're at. Okay? So, let's look at this guy. We could just find the slope again and again and again. That's certainly a totally legitimate way. Okay? Another thing you could say is, look, I'm increasing by 5 each time. And as I'm increasing by 5 on my x values, I'm increasing by 10 on my function values. That's a pretty darn good indicator that you have a linear function. But again, if you wanted to find the slope here, you would do 20 minus 10 over 5 minus 0, and lo and behold, you'd get 2. Similarly here, you would get 30 minus 20 over 10 minus 5, and you're going to get 10 over 5, which is 2. So, if these values are changing at a regular rate, the same as these values, you're going to have the same rate of change. Okay? So we'll say yes right here. Now this guy's a little funkier. Okay? Notice my x values are not changing on any regular intervals. These are changing by 100. This is by 200. This is by 300. So let's be careful here. Okay? Let's find the slope containing these 2 points. Do you all agree you get the change in your y values over the change in your x values? And we get 50 over 100, which is 1/2. Okay? Now let's find the slope containing these 2 points. Again, it's the change in your function values over the change in your x values, but now we get 50 over 200, which is 1/4. So do you see how here the rates of change are different, and therefore we'll say no. And on that note, have a good day. That's it for 1.3.